Hello, in this video we will be continuing on from where we left off and deriving the Black-Scholes model. So recall previously we were trying to solve these two components which we arrived at to be the Black-Scholes model, and we have solved in the previous video this part of the equation, which was the expectation of the indicator function. Now, what we will be doing is figuring out the risk-neutral expectation of the stock, given that the stock at time capital T is greater than the strike price K, filtering on all the information we have up to time little t. So what we will be doing is just ignoring the fact right now that we are dealing with risk neutral expectation and just simply deal with normal expectations. We will deal with the issue of risk neutral expectations in the future, but for the time being, we will just assume that we're dealing with the normal conditional expectation. So we have the following equation, which we would like to solve. So we already know all the information up to time little t, and therefore we cannot simply say what is the expectation of s of capital T and just figure out the expectation based on no information included up to time little t. So we have to account for that stock price. So let's begin by just modeling the stock price according to the Black-Scholes model, where it follows a geometric Brownian motion, and therefore S of capital T can be interpreted as S at time little 0 multiplied by e to the power of mu multiplied by t plus sigma multiplied by the Brownian motion, given that S of capital T is greater than K, filtered on all the information up to time t. So as I said before, we cannot really, it would not really be right for us to simply compute this expectation without taking out, without accounting for the fact that we know what the price of the stock at time little t is. So to account for that, we're just going to manipulate this equation as we did in the previous example, where we found out that this is equivalent to saying st is multiplied by e to the power of mu multiplied by t minus little t plus sigma multiplied by wt minus wt, given that the indicator function is true. Now, since s of little t is known and mu is simply a constant and time is a deterministic function not dependent on anything, we can take this part of the equation outside the expectation. And we would be left with the expectation of e to the power of sigma multiplied by wt minus w little t, given that st is greater than k, given all that information up to time little t. So we basically now have it such that we have a quantity which we are trying to find the expectation of, but only on the condition that a different quantity, s of time capital T, is greater than k. So the way that we can resolve this is by changing what st and k are but in terms of the Brownian motion. And we already have that figured out because in the previous example where we were trying to find the expectation of the indicator function and arrived that this is equal to the probability of st being greater than k, we realize that this is equivalent to saying that the Brownian motion is greater than this quantity over here. So in essence, we can say that st being greater than k is equivalent to the Brownian motion increment being greater than this quantity over here. So what we'll just do for ease of just writing stuff down in the future, we will call this quantity W and we'll call this quantity W bar. So rewriting this equation, we have it such that e to the power of mu t minus little t, the conditional expectation of e to the power of sigma W, given that W is greater than W bar. And we notice that the filtration will be no longer of any value because having known all the information up to time little t will change nothing within this expectation because we know that the Brownian motion is independent of the past. So we can simply have that no longer as a conditional expectation, but as a simple expectation. Now what we're going to try to do is just transform this expectation into the integral to basically be able to solve it. And the expectation of that is equal to the integral going from W bar, because that is what the indicator function over here is telling us, is that we want the expectation of this given that the Brownian motion is greater than the quantity W bar up to infinity. And someone might ask, why are we dealing with an upper bound of infinity? Well, it is because the Brownian motion is a normal distribution, and a normal distribution has bounds of negative infinity to positive infinity. The only reason we don't have a negative infinity over here as the bound is because of the indicator function. And continuing on, we simply have this. And if you recall, simply again, Brownian motion is a normal distribution. Therefore, we will multiply this by the PDF of normal, which is 2 pi sigma squared e to the power of negative a half x minus mu, W in this case, minus mu, divided by sigma, all of which is squared. Now I'd like you to draw your attention to sigma and to note that this sigma is not equivalent to this sigma over here. So the reason why is because this sigma was obtained as the volatility of the stock, which we arrived from over here. So and this volatility over here, or rather variance because it's squared, represents the volatility of the Brownian motion. And the volatility of the Brownian motion and the volatility of the stock itself are two different things. So what is the volatility of the Brownian motion? Well, this is a known fact. We don't know what the volatility of the stock is. We just have right now we just have a random constant. So, but we know for a fact that the volatility of the Brownian motion is, or rather the variance in this case, is the time increment. Also, that mu is not the same thing as this mu, because this mu is based on the expected value of the stock, while this mu is the expected value of the Brownian motion, and the expected value of the Brownian motion is 0. So we can simply have this as W and replace the volatility with the square root of t minus t. Square root of capital T minus little t. Now, what we're going to do now is standardize it, and you'll see how that helps in just a second. But I'll just go through the standardization a bit in depth because before I used to have that problem where I was like not really sure what was happening when we were standardizing stuff. So to standardize, it's a very simple process, i.e. basically what we're trying to do is get the mean to be 0 and a variance equal to 1. So in this case, to standardize W, which is the Brownian motion, we have to divide it, but we have to subtract the mean. However, the mean is 0, so simply we need to divide by the variance, or rather the volatility, the standard deviation, which is the square root of capital T minus little t. And that basically will give us a standard normal. And we'll call that standard normal x. So we can simply say that this is our near standard normal. So we will simply replace W divided by the square root of t with x. And similarly, we will replace W over here with x multiplied by the square root of capital T minus little t. And we also need to change the small infinitesimal increments of the Brownian motion to be the increments of the new standard normal. So to do so, what we will do is simply move the square root of t to the other side, and take the derivative of the Brownian motion with respect to x. That will give us t minus as the square root of t minus little t. And moving stuff slightly more around, we get the following. So dw is equal to dx multiplied by the square root of time little t. And we notice that this would cancel out with the denominator over here. And that makes sense mathematically and logically, because now the variance is equal to 1. So hence we would have this equal to simply 1, and it would just be 2 pi multiplied by 1. And hence we have standardized it. One very important thing to not forget is that the bounds of the distribution now will change as well, since we have standardized the Brownian motion. So we set that W is equal to W bar to be the starting point. So let me write that down. And however, now we are dealing with x. We are no longer dealing with w, because we're basically summing over the x-axis you can think of, no longer the w-axis. So we know that w is equal to x multiplied by the square root of capital T minus little t, and that is equal to W bar, because this is simply equal to this, and therefore this is equal to this. Hence, the lower bound should be the following. So now that we've done that, we're just going to make it a little bit neater and combine the exponentials together. So we have st e to the power of mu multiplied by little t multiplied by the integral of square root of t minus little t up to infinity. 1 over the square root of 2 pi e to the power of sigma multiplied by x t minus a half x squared. And let me just start a new page. Just copy this information over here. Paste it here. Okay, so now we're just going to focus on the exponential. And what we're going to do is the following. We're going to have negative x squared, and we're going to basically sub this part of the equation inside the brackets over here. So in essence, we're just multiplying it by -2 to account for adding it inside of the brackets here. So multiplied by 2, multiplied by sigma, multiplied by x, multiplied by t minus t. And basically we're trying right now to complete this square. So all we're gonna do is simply add the component which completes it. So in this case, that would be this sigma squared multiplied by t minus little t. But because we've added something, we also have to subtract it. And by subtracting it, we basically have not changed the formula. This plus this is 0. Now what we're going to do is take this part of the equation outside, and we would basically be left with writing the whole formula again. We would have st e to the power of mu multiplied by capital T minus little t, multiplied by the integral of w bar over the square root of t capital minus little t to the infinity over the square root of 2 pi e to the power of negative a half. And focusing on this part of the equation, we can simply realize that this is a square. So we can simply have this as equal to x minus sigma multiplied by the square root of t minus t all squared. And we are left with this component, which we took out of the negative half. And that will cause it to become e to the power of 2 multiplied by sigma multiplied by sigma squared t minus little t. Okay. Apologies, I got confused for a second. This is going to be, because we're taking it out of the equation, so we're simply multiplying it. I got confused, sorry about that. So in essence, we would simply have it as a half multiplied by sigma squared multiplied by capital T minus little t. So what we'll be doing next is basically, sorry, this is dx. I have to be consistent over here as well. So basically, we can take this part of the equation outside of the integral because it is simply a constant. We assume that volatility is constant in the Black-Scholes model. So taking it out, and we can combine it with this exponential over here because they have a common factor. So we would have it as u plus a half multiplied by sigma squared. And remember that sigma is the volatility of the stock. And multiplied by capital T minus little t multiplied by the integral of the square root of the lower bound being w bar divided by the square root of capital T minus little t, and the upper bound being infinity, multiplied by the PDF of a normal distribution, which is simply what we have over here. Dx. And now what we're going to do is standardize again. So we're going to call this part of the equation to be y. So in essence, y is equal to x minus the mean, in this case, if you want to think about it, being the volatility multiplied by the square root of capital T minus little t. And we don't have to divide by a volatility because the volatility, we've already established it to be 1 in the previous step. So now what we do is we also have to say that differentiating x with respect to y would give us simply 1. So if you think about it, if we move this part of the equation to the other side, so we have x is equal to y plus the sigma multiplied by the square root of t minus little t, and we differentiate that with respect to y, this part of the equation. So y will differentiating y will simply give us 1, and differentiating this with respect to y will give us 0, and hence we just simply have 1. So having done that, what that basically gives us is that there isn't, so dx is equal to dy. That's all that is saying. For the lower bound, we assume that x is equal to w bar c minus t is the lower bound, but now we note that y plus sigma multiplied by the square root of t, capital T minus little t, is equal to x, and therefore this will be our lower bound now that we have standardized this equation again. So we can change that to this. To be our lower bound. And hence we simply have the integral of a standard normal distribution going from the range of this quantity over here up to infinity. So if you think about it, graphically speaking, we have a normal distribution, and we're saying that here is the quantity W bar over the square root of t minus little t minus the square minus sigma multiplied by t minus little t. And we're saying everything greater than that, we're summing, and that is this part of the PDF. That's all we're doing. We're basically summing this portion of the PDF. Now, again, with as before, the way that we function with normal distributions is that we usually have something basically the normal distribution of x represents all the values which are less than x, not greater than x. So we just have to accommodate for that fact, and we will do so momentarily. So let's just rewrite this a little bit in a neat format. So let me just copy this to over here. So we have finally the stock price multiplied by mu plus a half sigma squared multiplied by t minus little t multiplied by the integral of that quantity. So now we're just going to say that so that integral where we're summing everything greater than this is equal to 1 minus the normal distribution of that quantity. Let me write it down. W bar over the square root of t minus little t. And because of symmetry, we know that 1 minus the normal distribution of this quantity is simply equal to the normal distribution of the negative of that quantity. So we would have, let me just try to copy this. So writing it down again. Okay, so what we're just going to do now is expand what that value of W bar is, and to do that, just recall what was W bar in fact. So going over here, if we have in this case W bar, then it'll be log of K over ST. So focusing on this part of the equation, we would have so log of ST over K, because there's a negative sign, and that we can, and basically logs, if we're dividing and we have a negative sign, we can simply switch the order, and that gives us the equivalent thing. And we would also have plus instead of minus as before, because we have a minus over here, and we would have mu multiplied by t minus little t, all of which is over to sigma multiplied by sigma, and we have now this part. So we simply multiply that by sigma plus sigma t minus little t. And combining one second. X minus mu. And because I've included this to be under the denominator, I also have to multiply it correspondingly by sigma multiplied by the square root. 1 second, sorry, I'm a bit confused here. Do we got this? And this is W, and this is divided by the square root of T, and this is sigma. Okay. So what I did wrong was I was just copying the quantity which we said over here as W bar divided by the square root of capital T minus little t minus sigma multiplied by the square root of capital T minus little t. I just did not square root this part of the equation over here. So yeah, sorry about that. And I just have to fix my mistake. And now if I try to combine them both under the same denominator, I would get the following. And that slightly simplified would give me and we will just write the left part of the equation over here. Whew. So that is what is the expectation of the stock price at time capital T, given that the stock price is greater than K, filtered on all the information up to time today, with the assumptions that the Black-Scholes model holds, which include constant variance, constant mean, and the fact that the stock prices follow a geometric Brownian motion. So thank you very much for listening. I'm sorry about the confusion that I had in a couple of times when I was trying to derive this. I hope that you can understand it, and if you have any questions, please don't hesitate to ask in the comments. Thank you very much for listening.